Start recording. All right, so we are recording using OBS, so Zoom can crap out and it wouldn't impact too much. All right, so the first thing I want to do is to kind of go over what Folsom Lake has been doing. So Folsom Lake has been they started an AI discipline. So it has its own designator. There are classes that starts with AI on it. So for people who are interested, you can kind of look into this. They have 300, which is Introduction to Artificial Intelligence and Machine Learning. And then they have specific things about ethics. And this one is about machine learning and deep learning, focusing on the differences, mathematical foundations, and practical applications with no mathematics prerequisite. Yes, that makes the class a little bit challenging to teach and also to take. This one has a prerequisite of AI 300, which is the first one all the way back here. So so ARC does not have that. Okay, we are not. I have not started the AI discipline for a few reasons, but I am using AI. Okay, so what I want to do today is to kind of go over the questions in exam two. So that people have a general sense of how they did in the exam. Okay. Um, and I'm going to demonstrate how to do it using AI and what are the things that you can run into when you use AI for this sort of thing. So this is my chat GPT conversation that started off with me being lazy and just copy and paste the markdown representation of the entire exam and just posted it to chat GPT. So these are all the questions of a particular variation of the exam. And then I ask it, okay, so answer those questions. And it answered one of the questions, like question five, I think. Um, and then I specifically said, okay, what about the other questions? I wanted to, can you attempt question number one? So in this particular exam, this is the question number one. X is always the same, but R is different depending on which version of the test you get. And then the how C0 and C1 are defined can also be different. So part one, it also, so ChatGPT was able to separate all the parts and know what to do with each part. So in this case, part one is asking if the cardinality of the set returned by C0 as a function using R and X as the parameters, if that is zero, which means if if the function returns an empty set, I'm asking, okay, which relation property can be confirmed in that particular case? So ChatGPT was able to quote from the question itself, how C0 is defined. Okay, can I answer your questions? Okay, so because I can hear you, which means other people can hear you too. So let's do it after class, maybe. Okay. So in this case, EF, in is an element of whatever C0 returns, if and only if ERF and not FRE and E does not equal to F. This identifies asymmetric pairs where one relates to the other but not the reverse. Um, and we never really use the term asymmetric pairs. Um, we use the term anti-symmetry. So this one is, it does not quite use the term that we use in class because I did not upload my notes ahead of time. So it doesn't know what term to use. In other words, if I give this exam as an online asynchronous class and somebody came back with the term asymmetric pairs, I go like, we never talk about this term in the class. Where did this come from? So I would definitely get suspicious as a result. But the question is that correct, where one relates to the other but not the other way around? The answer is actually correct. Okay. In other words, in our term, it would um, it would identify. So the answer is actually incorrect. Um, well, okay. So the final answer is correct. Okay, because if the cardinality of C0 of Rx is 0, which means if it is an empty set, then the relation is confirmed to be symmetry, that there's symmetry in the relation. Okay. Um, so do we have any questions about this answer? Yes. Um, but we never use the term, asymmetric pairs. Yeah, so it is correct that the C0 is identifying asymmetric pairs. So that part is kind of correct, but I wouldn't even say that is those are asymmetric pairs because it will only one of them will show up here. In other words, in this particular case, what do you think C0 is going to return? It will return 2, 1. There's one more, 1, 0. So it will return two elements in this case. 1, 0 is one of the elements in C0, and then 2, 1 is the other one. 0, 2 would not be in it because 0, 2 and 2, 0 are both present. So there are two elements in this particular case, what C0 is going to return. So the part one is symmetric. That is actually correct. So part two is looking into this particular way of defining C1. So this one is, I try to mask it as much as I can, try to make it confusing. But at the end of the day, we still have three things that we're trying to relate. And there's only one relation property that requires three things to relate. So that's transitive. That's right. So in this case, it answers here with transitive. That is also correct. Now, what is interesting is part 3 and 4, because parts 3 and 4 want you to give me the exact answer of what C0 and C1 would return in this case. So this time, part 3, blah, 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 it is correct. Okay, it doesn't have a problem with part 3, but part 4 is actually incorrect. So in this case, part 4, it returns 0, 1, 1, 2, which is actually incorrect. So let's go back and do it by hand and find out, whether what it should be. So this is the relation. We are basically looking for a counterexample of why it is not transitive. Okay, so we just look at this. You can, I assume you guys know how to look for evidence that the relation is not transitive. So you can basically just do the eyeball thing. 0, 2, 2, 0, 0, 0 is here. 2, 0, 0, 2, 2, 2 is here. So we are good there. 0, 2, 2, 0. Okay, we got that already. 1, 0, and then 0, 2, 1, 2 is missing. So we have a problem, right? So 1, 2 is should be in the set of C1 because it is a counterexample. Because, okay, does everybody understand what I just said? Okay, so that's one. And I think, is there another one? So we got 2, 1, 1, 0, but 2, 0 is present, so that's not a problem. Hmm? 0, 2, and 2, 1. So 0, 1 is also missing. So let's see whether the answer here is correct because I know it got one of them wrong. So is it 1, 2 or 2, 1? Okay, let's double check. So let me write down on the whiteboard what the answer is. So it answered 0, 1 and 2, 1. 1, 2, 1, 2 and 0, 1. Okay. All right. So let's go back to the relation and see whether it got it right because I think it got one thing in the truth table wrong. So we will double check. There we go. All right. So 0, 1 is that a proper answer? We have 0, 2, we have 2, 1, 0, 1 is missing, and that would make it, hmm? And then 1, 0 1002, but 12 is missing. Okay. Well, in that case, oh, okay, it's the first part that got it wrong. Okay, so C0 it has it wrong because it thinks 02 is in C0. So let's look at the C0 and see whether it got it wrong or not. So with C0, we are looking for counterexamples that it is uh, symmetric. 02 is definitely wrong because we see 0 here and 20 is also here. So it got the answer wrong. Okay, that was my mistake. Yeah, I remembered incorrectly that they got the second part 4 wrong, but they actually got part 3 wrong. So, okay, so here's the interesting part is I noticed that it is wrong. So I said, I instead of telling ChatGPT that it was wrong, I said I do not understand why it is there because I want ChatGPT to explain that. So it went through the whole explanation and it just walked it through because if I said it was wrong, it would try to find out why it was wrong and try to explain that. If I said I don't understand, it would assume that it was right and then try to explain its way away. So it did, blah, 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 blah. Okay. And, oh, okay. So, and then it found its conclusion because, as I asked the question, it found that, 02 should not be the part of the answer. In other words, the question prompted ChatGPT to kind of double check things, and then it realized that it was wrong. And then it has a correction. Earlier, I incorrectly concluded included 02 in C0, and that was a mistake. So let's recompute, blah, 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 blah. And then it now has the correct answer. So now this is the important part because what I wanted to do, what I wanted to know was how it made the mistake to begin with. In other words, what you as a human needs to do is one, you need to know what the answer is supposed to be. Okay, ChatGPT or other tools may be able to give you an answer in a short amount of time, but you need to be at least be able to spot check whether the AI is giving you a reasonable answer, which means you need to know how to find the answer as well. Is that okay? So there's no replacement of what we do. We can potentially use it to save some time, but it cannot replace what we do. Yes, because I want to assess how much it can do and whether it can get something wrong or not. And if it does get something wrong, why does it get it wrong? In other words, okay, so most AI or neural net based AI mechanisms is essentially a black box. It is not like there's an algorithm and we can apply hard logic to analyze the algorithm and we can know ahead of time whether it's right or not, okay, and if it is wrong, why it is wrong, okay. There's no way to do hard logic on a neural net based approach. So the only way you can find out whether something will work or not is really to test it, is to try out and find out what it's doing and whether you get it right or not. In this case, it was wrong, but I was curious about why it was wrong, so I asked ChatGPT itself why it got it wrong in the first place. So I asked it how was the mistake made in the first place. The candidates table was incorrect because you indicated that not FRE is false when E equals to 0 and F equals 2 because it was listed here. So that's an interesting question to ask a LLM, and the answer is also interesting because it actually explained away how it got it wrong to begin with. Blah 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 blah. Okay. Reflection. The AI was able to do its own reflection. Here's a classic example of cognitive error in Boolean reasoning. When dealing with symmetry looking elements like 02 and 20, it is easy to forget to double check the inverse. And negation over a condition must be read carefully, especially with asymmetric definitions like what we have in C0. In other words, it is making the same kind of mistake that a person would have made. And this is not the first time either. I was using ChatGPT as a tutor for CISP 310, and initially it would make exactly the same mistakes that a person would make. Certain things are off by one, or it is forgetting about certain things. It would make exactly the same kind of mistake. So then I asked, probe a little further, and I said, I want to understand why an LLM like ChatGPT makes this kind of mistake, which resembles the mistakes made by people. Can you explain this? And it went on and explained blah 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 blah. And I think, if you are, considering using AI, to solve problems and whatnot, um, this is the kind of inquiry that you kind of need to do, and give it a test, knowing what the answer is supposed to be. Then you compare the answer from the AI to the proper answer. If they are different, you try to find out why they're different. And in this case, ChatGPT also said, how to help prevent this from happening. In other words, it says, if I were to include, okay, the step-by-step instruction of using formal evaluation, um, then it would know how to use a truth table as a part of the mechanism, and then it would not be as prone to making this kind of mistake or not. So I think this may be helpful to some of you. To me, it is just a curiosity. That's all it is. But I think, if you need to utilize AI, as a part of your job, asking this kind of question, to probe the LLM itself to explain why it makes mistakes in certain specific cases is helpful because it will help you refine your prompts. The next time you prompt it with a similar problem, now you can go like, okay, I know this prompt is not working because I'm not giving it enough information, or I'm not breaking up the steps enough that it can kind of go through the very mechanical steps and maintain the context in a better way. Um, and it also explains other things that are important, like the lack of persistent scratch pad memory. Um, so what you can do is now say, okay, how can a prompt be engineered so that part of the answers or part of the reasoning steps would maintain its own persistent scratch pad memory? Because now before this, I did not know the term. Okay, I did not know the phrase of persistent scratch pad memory. Now that I know that term, I know how to use it because I can now query how do I make sure that the persistent scratch pad memory is maintained in the attempt to answer a particular question. That is how I would. This is what I think an AI class should teach. It is, how do you use AI? How do you refine? How do you find out whether there's a problem? And if there is a problem, if the answer is not what you expect it to be, how do you diagnose, okay, and refine and change your prompt accordingly to the best ability so that you can get the correct result? So are we good so far? All right, cool. So now we can kind of go over the other questions. Okay, so let me go back to that exam 440, and this is exam 2. All right. So question 1 is from here. Okay, so we are done with that one. So now we deal with question number 2. So question number 2 has C0 defined as this one, which is different from the things that we have seen before. So what do you think C0 is corresponding to? In other words, if C0 is returning an empty set, what does it mean? This one is about symmetry. It was done already. Okay, so this is not symmetry. It looks a lot like symmetry, didn't it? That was me doing my job, making it look confusingly similar. It is asymmetry. It is asymmetry. So when you have ERF and FRE and E does not equal to F, it is a counterexample of asymmetry, anti-symmetry, sorry, anti-symmetry. So the answer to the first question is anti-symmetry or anti-symmetric. What about C1? This C1 is, oh, it's the same as one of the ones we have seen already. So this is symmetry and this is anti-symmetry. And you can see how they are different only by one term. One has FRE, the other one has the negation of FRE. Now, I did another trick here because in the case of symmetry, this is not needed, but I put it there just so that they can look about the same. Yeah, so Tack is doing his job, making things look confusingly similar when they do not need to look so similar. All right. So now what does C0 return in this case? In other words, what are the counterexamples that R is not anti-symmetric? It'll be an empty set because it is anti-symmetric. But C1 is going to return one element because it is not symmetric. It is not symmetric because we have 0, 1, but 1, 0 is missing. So 0, 1 is the only element that should be returned by C1 as a set in this case. All right, moving on to question number 3. So question number 3 defines C0 this way, which is something that we haven't seen before. So we will try to interpret what does C0 returning an empty set mean in this case. What does it say about the relation? So in this case, it is the negation of the or between ERF and E does not equal to F. So what does that mean? Yep, you can simplify by De Morgan's law. Okay, so what do you get when after you simplify by De Morgan's law? So I'm going to use a little scratch pad here just so that I can show you guys how to do the derivation. You probably should know how to do it by now, but I'm going to also show it on the screen. So let me move my little notepad over here. All right. So we have the negation of ERF or E does not equal to F. Okay, so I'm going to use the um, C notation here. The parentheses are really not needed. Okay, the or really has the lowest priority in this case. So we'll go ahead and say, okay, what does that mean? So this negation is really applied to both of these. So now we end up with E not ERF and E equals to F. So there's a implicit and here. So I'm going to just really specify and as in and here. Okay, so what does that mean? It is reflexive. Yep. hmm So that means C0 returns a non-empty set if the relation is not reflexive. So in this case, is it reflexive or not? Well, we have 0, 0. That's good. We have 1, 1, which is good. But 2, 2 is missing. So that means it should return 2, 2 in when we evaluate C0, it will return 2, 2 as a 2 tuple as the answer because this relation is not reflexive. That is correct. So the answer to number 1 is it is reflexive. And your question would not be the same. Okay. In other words, I have ways to scramble which question is asking about which property of a relation. So, yours is going to be most likely to be different unless your question number is, I mean, you're actually getting exam to version 00. Yep. All right. What about C1 in this case? So C1 in this case is, we have seen this already. This is just anti-symmetry. So that means, is this anti-symmetric? This R is not anti-symmetric. So that means C1 should have returned an empty set. Is that okay? All right. And number 4 is the last one, of this nature. So let's go ahead and finish this up. I think it introduces one more property, which is comparable, because there are 5 of them, right? We have seen 4 out of the 5, so that means that one of these it has to be comparable. So we'll take a look at which one is comparable. So the first one is, oh, this is the one that we haven't seen, right? So that's the one that is comparable. So in other words, C0 returns a non-empty set if R is not comparable. Why? Because the relation, I mean, the qualification to be a member is not ERF and not FRE. In other words, we're looking for two elements in X where they do not relate to each other at all. So that's basically the essence of comparable. So now we look back into this R and we ask, is it comparable or not? And if not, why is it not comparable? 0, 0, 0, 1, 0, 2. So between 0 and everything else is fine. So now we look at 1. 1 relates to 2, good. 1 relates to 0, good. But 1 does not relate to itself. So 1, 1 would be one of the elements at least returned by C0. And then we look at 2. 2 looks like it's okay. 2 relates to 0. 2 relates to 1. 2 relates to itself. So 2 is good. So the only element returned by C0 in this case will be 1, 1 as a 2 tuple. Is that okay? The other one we have seen already, this one is symmetry. So now we just look at this and ask, is it symmetric? No, it is not. 0, 1 would be at least one of the elements. 0, 2 is fine. 1, 2 is fine. So 0, 1 is the only element returned by C1 in this particular question. In this one, let me check. So in this one, oh, 0220 should be part of C1. You're correct. So it is not anti-symmetric because 02 and 20 are both here. Yep. But it will return two elements, not just one, because uh, because when E is 2, F is 0, it would meet this requirement, but the flip one would also meet this requirement. Yep. All right. So that's questions 1 to 4. Any questions about those 4 questions? Nope. Was it like easy, kind of easy, or a little challenging? It's okay. Okay. All right. So now we move on to number 5. Number 5, it reflects how lazy attack really is because I did not change the question at all. The only thing I changed is, or the only thing that I scrambled is psi itself, but the question itself stays exactly the same. So that means you just have to evaluate psi in this case and fill up this truth table. Does anyone want to watch me fill up a truth table again? You do? Yeah, so this one is just kind of tedious. You just have to evaluate for each row what psi is going to return and fill this up and just be careful about the whole thing, double check. There's nothing too abstract or difficult about this. Derive the CNF according to psi. You can use Boolean algebra, blah, 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 blah. Okay, so that's the only part that may be a little bit challenging. Okay, so let's go ahead and do just that. Uh, there we go. All right. All right, so this one is, I can just copy and paste, save myself a little bit. Ah, did not mean to scroll at the same time. There we go, Control C. All right, there we go. All right, so we want to convert this into a CNF, okay? I'm just going to do it the way that I usually do it, which is getting rid of the implication first. Okay, so we take this, we copy it and paste. So the implication becomes an or, and then we have to negate the left-hand side of that. So that would be this one. And now we can do a simplification because we have double negation. Okay, so copy and paste, get rid of the double negation like that. And I think we cannot apply De Morgan's law anymore. Okay, so now we look at this and we ask, okay, what can we do with this? Well, we know it boils down to distribution, okay, because when you cannot apply De Morgan's law and there are no more implications to convert to negation and or, the only thing we can do is either simplification or distribution. So in this case, what distribution are we going to use? Let me remove the redundant parentheses first, so it's easier for you guys to see what it looks like right now. So this is definitely not CNF, okay? In fact, this is kind of the opposite of CNF because we have a disjunction of conjunction and a conjunction over here. So what are we going to do? Okay, so let's look at the pattern, okay? We have A plus B, AB plus CD. And in Boolean algebra, okay, the addition is actually a disjunction, the multiplication is actually a conjunction. This one can be FOILed into A or C, A or D, B or C, B or D. Okay, that's one way to do the FOIL. And if you were to apply this to this thing over here, you would end up with a CNF already. So that's what we're going to do. Basically, I look at not P as A over here. I look at Q or R as B over here. I look at C as not R over here. And then I look at Q as D over here. And once you perform the FOIL, you will end up with a CNF. And because the question did not ask you for the most simplified version of the CNF, so if you just do a FOIL, you're done. That is the answer. So do you guys want me to actually carry out the FOIL, or you guys go like, okay, we know what to do with this? We good? All right. So moving on to the last one, which also, what? Hmm? Oh, okay. Okay. Because I cannot tell whether this means we're good to go or yes, I want. Okay. All right. All right. So we can do it. We can just do a FOIL, right? Not P or not R. We have not P or Q. Then we have Q or R or not R. And then we have Q or R or Q. Okay. And you can leave it like this. It is already CNF, but personally, I would do it like one more step just because I do not like things that look like this. And then this is going to simplify to a 1, which is it's because R or not R is 1. And this one just simplifies to Q or R. And then we simplify the 1 out of the conjunction. So we are left with uh, Q or R. Yep. That would be the final answer that I would give, but it is not required. Okay, so if somebody figure out and go like, okay, this is my final answer, I would have counted it as a 100% answer. Is that okay? All right. So now we are moving on to number 6, and that also reflects the laziness because it also is not changed other than what is included in phi. Because the format of the question did not change, the approach to answer this question also will not change. Okay, so now what we need to do is to find out what is not phi. So not phi is just going to be the negation of this thing here, right? This entire thing is phi. So I have to be careful to also include the negation. So now we are just negating this entire thing, and then we end up with double negation. So double negation goes away. So that means what is left is already a CNF. In other words, I am testing whether you can convert something into CNF using question number 5, but question number 6 does not need that at all. Okay, just like in the practice exam. So now we have to combine psi and not phi. Okay, so that becomes the longer CNF. And the way I do it is I would kind of spell out things. So psi itself has not P or Q. It has Q or R. It has P or not R. And then we combine that with not phi. So not phi is contributing Q or not R. And it's also contributing not Q or R. There we go. I'm just double checking, make sure that is correct. Yep, that looks good to me. So now the idea is you have to come to one of two possible conclusions. One is, oh, you can simplify it all the way to false. Now you have a contradiction, then you can conclude that phi is a theorem of psi. Or you try your best, okay, and you cannot get to false. And any further resolution steps will only get you something that you already have. So you're at a dead end in that case. In that case, you can conclude that phi is not a theorem of psi. So now we just go for the derivation. Um, so it's all about singling out things, right? So we want to see what can we single out first. Hmm. So if I use P, hmm? Get R out of there. Okay, so which two do you want to resolve? 2, 4. Okay, so with 2, 4, we will only have Q left because we're using R, to be the quote-unquote connector, because one has R, the other one has the negation of R. So whatever is left is just Q, but Q or Q is just Q. So now we have singled out Q. So once we have singled out Q, we can use that Q to single out some of the other stuff, because now we can use 6 and 5, right? 6, 5 would resolve, and we would have R left. Now we have R, we can use R to single out a bunch of other stuff. So anyone with a not R, we can single out things. So 3 can do it, right? So 3, 7 can resolve. And if we are to resolve those two, we would have P left. And then 4 would also do, right? So 4 and 7 would also resolve, which ends up with Q in it too, but we got Q already. All right. So now what do we do? Um, I'm fairly sure that this will resolve to false. I'm just double checking whether I copied things incorrectly or not. I did. I did. Yeah, it is. That was my bad. Okay, my bad. I copied and pasted incorrectly because that there's a negation here. Okay. All right. That's my bad. I have not used one yet, so it's okay. I don't have to change anything here. All right. So given that is the case, it is cool because now I can say, hey, 1 and 8 would resolve, and we would have not Q left, and then 10, 9 and 10. Okay, this is number 11. 9 and 10 would resolve to false. We're done. So now the conclusion. Yes, go ahead. Because that's how we use proof by contradiction. So proof by contradiction says if phi is a statement and you want to know whether it is a theorem of psi or not, you have to negate phi first, turn it into a CNF, and then merge that CNF with psi as a CNF, and then try to resolve to false. The implication, because resolution itself is implication. Because resolution itself, go ahead, sorry. It's not explicit because every time we perform resolution, these are all implied by the 5 that we started off with. Because resolution, if you look up how resolution is defined, it says, if you have something that looks like this, it implies P or R in this case. So the implication is already here. Every time you apply resolution, the result of the resolution is actually implied by what you started off with. So that means this is a long chain of implication, which also means this eventually you started off with these five given ones, they all basically imply false. But because the implication itself is true, so that means whatever you use to imply the false has to be false as well. In other words, this conjunction has to be false. But because if that conjunction is false, then proof by contradiction says um, phi without the negation has to be implied by psi. That's the essence of proof by contradiction. Any questions? Yep. Yes. Yep. That is part of what is needed. Okay. And we kind of talked about that a little bit in when we worked out the exam from the previous. No, no, not just the homework, but also the previous, the same exam, but in the previous semester. Yep. Yeah. Why can we not use 4, 5 right away? Well, let's see what happens when you use 4, 5. Okay, so we can just throw in 4, 5. Maybe mm, we are not going to number that. Okay, so we'll just say 4, 5. So now you have a choice. Which one do you choose to use as the connecting variable? You can only use one. You cannot resolve two variables at the same time. So that means 4, 5, you have a choice. You can end up with Q or not Q because you are using R to annihilate not R, or you can also use Q as the connection variable. Then you would end up with not R or R. Either case, you end up with true. So it is not, you can do the resolution, but the result of the resolution is not helping us in any way because it is just true. Is that okay? Okay. Yep. Does everybody understand what I just said about? Okay, cool. Yes, go ahead. What do you mean by in what context are you saying always applicable? In theory, yes. So, but typically, if you can do a direct proof, then you would do a direct proof. But proof by contradiction can prove things that are much harder to prove directly. Like the sock example that I use in class, that would be pretty hard to prove directly. You can do it by looking at all the possibility and prove it that way, but the proof by contradiction approach is much easier. It is just a whole lot easier. Um, the pigeonhole principle is the other one. So you can prove the pigeonhole principle using a direct proof, probably using proof by induction, which we haven't talked about yet. But the proof by contradiction method is also a lot simpler because you have more pigeons than there are pigeonholes. But if you negate the theorem or the theorem itself, then you would end up with a clear contradiction because the given is you have more pigeons than there are pigeonholes. But if you negate the theorem, then you end up with a statement that says you have more holes than there are pigeons. So they cannot both be true. So there you have your contradiction. Yep. So the answer is yes, it is always applicable because the proof technique itself is logical. But whether the steps can connect to the contradiction or the false that you need, that varies depending on what theorem you're trying to prove. In computer science, a lot of proofs are either um, proof by contradiction, proof by induction, or a combination of the two. So those two are um, okay. Let's just focus on proof by contradiction. It is a very important technique to prove things. All right. Any other questions about the exam? So do you guys get a general sense of how you did in the exam because of this? Okay, cool. All right. Excellent. So now we are moving on and back to where we left off, I think with big operators. We were talking about counting, and as a result, we had to go to big operators. So now let me go all straight to where we were at, which is here. All right. Um, Omega. So let's read this a little bit. The outcome set omega of an experiment of M trial is just the Cartesian product of the outcome set Ti, where I is an element of, from 0 to M minus 1. That's just notation, okay? In this case, in the cases where the outcome set of each trial T of I is independent of the other trials, blah blah blah. However, with the concept of without replacement, then you are losing one element every trial. In other words, if you have six marbles in a bag, and I say, okay, take three marbles out, okay, and the ordering of which marble you take out first, second, and third is significant, then you have six marbles as your potential choices when you pick the first one. But when you pick the second one, it gets a little tricky, right? It's easy to see that we only have five marbles left. But which five marbles are left kind of depends on which marble was chosen first. So if the interest is not to figure out how many ways can we choose three marbles out of six from a bag, but instead I want to know exactly all the permutations of choosing three marbles out of six from a bag. Hmm, then we cannot use factorial and just numbers to calculate the number of outcomes, because this time we are actually interested in exactly what tuples do we get out of the experiment. Is that making any sense? Okay. And we already showed this, using a graph approach, right? Using a tree approach. Yes, we did. So you can kind of go back to the previous lecture and revisit the tree representation. Hmm? I have to reconnect, all the. I didn't even bring my tablet today, so no, I do not want to. I cannot do it again. I can do it on the whiteboard, but I cannot do it because the other one person is over Zoom. So you might want to review that, okay? You might want to review some of the previous lecture where I use a tree to represent, how that happens. So this time I want to represent the whole thing using an algorithm, okay? So here's the question. If we know how to do it using a tree already, why do we want to represent it using an algorithm? Because that's basically what these notations boil down to, okay? Even though it doesn't look like it, it is just boiling down to an algorithm. So why is that? Yes, exactly. Because if I were to ask you, here's a bag, the lotto tickets, okay? Perfect example. Okay? You have 69, if I remember correctly, is it 69 numbers for the five numbers to choose from? Um, and if ordering is important, because this one, is about permutation where ordering is important. So if I want you to give me all the permutations of choosing five things out of 69, and you try to do a gigantic tree, how many entries are we looking at? Now, it's only five, right? We're only choosing five out of 69. The problem is the branch out, okay? The first level would have 69 branches, right? And then for each node after the first level, you have 68 branches, and then you have 67, and so on. So the total number of branches before you hit the leaf nodes is going to be 69 times 68 times 67 times 66 times 65. Do you really want to draw that tree? So we want a program to do it, right? So we want to write a program to do it. So now the question is, how do we write that program? Yes. It's because sometimes, you want to keep track of all the possibilities so that you can say, okay, I observed this already, I can cross that out. Um, you know, it depending on what you're trying to do, right? Because sometimes you're not interested in the probability. You want to know what has not happened yet or what has happened. All right, so we are going to go take a deeper dive into these notations. So now we start with this notation here. What is omega I of t? So omega I of t is representing the outcome set of an experiment. The experiment has I trials, starting with t as a set, as the trial, as the possibility of the first trial. Okay. In other words, if I am asking you to take 3 marbles out of 6 and ordering is important, the 6 marbles would be t, and then the 3 would be I, because I is the number of trials, and then T is representing for the first trial, what choices do we have? Is that okay? Is the notation clear enough? Is that okay? All right. You can kind of look at this as a function that returns a set of tuples, and we want to figure out how the algorithm works. Yes, the big U. Okay, so we'll get to that part. I can give you some examples of what the big U does. Okay, so we will get to that. Um, so, but are we clear on what this symbol or what this function is going to do? Omega I of t. Choose, there are I steps. Each step is going to choose something out of t, and it is without replacement. That's basically what it is trying to do. And it is supposed to return a set of tuples because it's returning basically all the possible ways of choosing I out of t, and ordering is important. So I cannot use a set because I can use a set of tuples because tuples with tuples 1, 2, 3 as a tuple and 3, 2, 1 as a tuple are distinct. They are not the same. All right. So the way to look at recursion is, I'm gonna say this, and some people is gonna frown on this, but I'm gonna say it anyway. Lazy people will find recursion easy to understand and easy to implement. The reason why I say that is because lazy people would look at the simplest case and go like, oh, in what situation do I not really have to figure out anything because the answer is clear. If I'm asked to do this, the answer is like this, done. Okay. That's how I think of recursion. Okay. I think of the base case first. Okay. In what situation do I not have to think about anything? And here's the answer because it is really clear. Okay. So in this case, the base case is omega 0 of some t, and it is always going to return a set with an empty tuple. Okay, so let's try to figure out why that is the case. Because understanding why this is true to begin with is going to help you understand the whole concept of permutation and also how this algorithm is going to work. So this is basically asking you, and here's a bag of 6 marbles, okay? The same 6 marbles. And I'm asking you, and here's a little test tube, okay, with the same diameter as a marble. And I say, okay, here's a bag of 6 marbles, and this is a little test tube. And I want you to figure out how many ways can you choose nothing out of the bag to fill up this test tube over here. There's exactly one way. At the end of every single possible way to do this, you just give me back the empty test tube. It's like, this is the only outcome of that particular experiment. Does that make sense? Okay, so I hope that makes sense because this is how we figure out the base case of anything that is recursive. We look at the simplest possible case. Okay. Now, in some cases, it is hard to find what is the simplest case when integers are involved. Okay. When I say integers, I'm basically contrasting integers with natural numbers. The reason why there's a big difference between integers and natural numbers is integers do not have a natural starting point. Okay, 0 is not a really natural starting point because we have -1. So it's like, okay, what of the other side? Natural numbers on the other hand has a natural starting point. 0 is a natural starting point because there's nothing before 0. Okay, in this case, we also have a natural starting point because 0 is as low I can go. I cannot ask you to remove a negative number of items from the bag, right? Zero is as low as it can go. So that means zero is a natural case to consider when we want to find out, okay, what is the base case and what is the answer to the base case. So are we doing okay so far with this one? Okay. So knowing this is the base case, now we want to figure out the step. Okay. In other words, this is the step. Okay. I know how ugly it looks like, and this is a good time to talk about the big U notation. Okay. So let me segue a little bit and talk about the big U notation. And since this is not my tablet, I can't really use the big U notation here. So I'm going to try my best to approximate. So here's the big U, and this is a subscript of E in a set of we'll just give it a random set of 2, 4, and 19. Okay, and this is the big U on top. It doesn't look too big. Okay, fine. You guys want to look at something that's big enough? I can approximate that. Yes, ASCII art. How's that? Is that a big U? Big enough for you? Okay, no pun intended. So this is basically saying, okay, but I need one more thing here. So I need to define what are we doing with E, okay? So let's just say we multiply E by 2. Okay, there we go. So the result of this is going to be 4 because 4 is 2 times 2. And then we have 8, which is 2 times 4. And then we have 38, which is 2 times 19. Is that okay? Is this working? Essentially, okay, if I want to take this one to a slightly more abstract version, and I say, f of e instead, okay, so f is some kind of function that we perform to e. This would then be f of 4, f of 2, sorry. This would be f of 4, and this would be f of 19. In other words, all we're trying to say is go through everything in the set that is part of the original big U notation, go through every single element, perform whatever this function f is to each element. Whatever the result is, it's going to end up with the big union of all of those. So the proper way to say this is not even this. The proper way to say this is perform this operation, okay, f of 2, make a set out of its own, union that with the set that only has f of 4 in it, and then union that with the set with only f of 19 in it. The difference between what I had earlier and this notation here is if 2 and 4 ends up to have the same value after I apply f, the previous approach would say, but then we should only have 2 elements. How come you have 3 things listed in the set? This approach says, oh, we are just doing a union. Okay, if all of these map to the same thing, because f is a non-injective function, you guys go like, do you really have to use concepts that we have learned already in this semester? The answer is yes. Okay. So if f maps everything to exactly the same value, this would still be correct because we end up with only one single value of the entire union. Is that okay? So does that explain what the big U notation is going to do? Yes. Yes. But we are using set notations to express the method to get a set of all the tuples that represent the outcome of an experiment. Yep. All right. So does that help explain what the big U notation is doing? Yes. It's not adding because we are performing set operations, so there's no adding per se. Potentially, but not always. It's unioning. It's not adding. That's the unioning or the union operator, right? What is the all right, so let's try to answer that question. This is a very, very important question to answer because ultimately it ties into how you study. And that's important, okay? Not only for this class, but also for every class that you will take in the future, because we have already talked about what a union is. So the question is, one, where do we find it? And two, how do we maintain that knowledge throughout a semester? So yes, go ahead. It's in one of the first ones, right? We talk about set notations early on. So it would be the first one right after Boolean operators. So it's going to be over here, and there are a few versions of this. This is the hair splitting version of this, but we can take a look at this one. Splitting hair is what I do. Yes, go ahead. Oh, okay, that's all right. So look, if we look at this, union is defined here. So for all E is an element of the union of the set X and the set Y, if and only if E is in X or E is in Y. That is how a union is defined. I believe we went through some examples, which may be actually in the slide already. Uh-huh. Yeah, not this one. Okay. Okay, so let me give you a few different definitions of F and see what happens. Okay. In a way, yes, we're combining, but so is intersection. It is also a way of combining. Difference is a weird way, but it is still a way of combining because you're generating a new set from two given sets. So it is still quote unquote a way of combining. So, but you can definitely look at union and intersection as combining. So combining is not enough to describe how what we do with a union. So with this one, it really depends on how F is defined. So let me give you two extreme examples, but let me see. Yes, yes, but that's from an abstract operator perspective. We are basically performing a particular operation to everything that we are given with in the set, and then we are quote unquote combining or operating the outcome of each one using this operator here. Yes. Um, Well, Ilias is not here today because if he was here, he would have said he would have tried to use some JavaScript or Python example. So it is my job to do it now. Okay. I'm taking his place. Okay. So in JavaScript, okay, so I think this is actually helpful, okay, because ChatGPT actually understands JavaScript to the point that you can describe what you want to do and you want it to give you a solution in JavaScript. So um, yes, basically all web scripting jobs are gone. Here I said it. If your aspiration is to become, a developer, developing, web scripts and stuff like that, there are not really much of those jobs anymore. Period. Period. Done. Okay. Okay. So we'll take a look at JavaScript. So I will say, okay, let in this case let X be a set, okay, and we'll just do a new set And then the way you initialize elements in the set is to give it a tuple, and then we'll try to add all the tuples to the set. So in this case, I'm going to use exactly the same example. So 2, 4, 19 are going to be elements of the set that I'm going to call X. Is that okay? All right. So now I want to say, I want to define the function f. Okay, so we say function f of n is defined to be, okay, we'll just say return 2 times n, which is what we had earlier. Is that okay? So basically, I'm redoing the same example that we did earlier, except it is all in JavaScript actual code. Good so far? Okay, all right. So the big U notation in that case, okay, so let me go back. So we are dealing with exactly this big U notation here. So the code to do exactly that is going to be as follows, okay? So we basically end up with another set, which is the result. So I'm going to say result is a set, okay, is new set, okay, which initially is empty. And then what we are going to do with it is to have a whole bunch of union. And I need to look up how to perform union as a method in a set object. So because it is new to JavaScript, I had to implement my own method when I did all the set operations. But the new implementation of JavaScript actually has set and also union in it. So it is now part of the standard. Okay, so as I suspected, it is just that. So other is another set or set-like object. Okay, cool. All right, so we can go back here. All right, so now what we are doing is we're going to say, x for each, okay? And there is such a method called for each, which means um, you are going through every single element in X, and then you specify what you want to do for each one of those. So I'm going to say E and then this notation here. In other words, I'm giving for each a callback function. This is the shorthand of specifying a function in JavaScript where E is the parameter and this is the body of the function. So you can basically specify functions that are nameless in JavaScript and pass it as a callback. So for every possible E, it's going to call this function. Okay. So what we'll do is we are just saying, result is going to be, is union going to modify the object itself? Let me see. Return value is a new set, so it does not change the original set itself because it returns a new set. Okay, fine, that's okay. I just need to make sure. So result is result union with a set that has that single element in it. So that would be a new set, and we specify just one single element in it, which is f of e. And that would basically accomplish what we specified earlier in the example, but I need one more close paren here. There we go. So the earlier example that I gave you, where function f is just doubling the value of each element, is going to end up with basically this code here. Yes, there was a hand earlier, which, yeah, go ahead. Well, set has always been a part of JavaScript. It's the union operator or the union method that may or may not be. Maybe, I don't know, but let's go with this one first, okay? So does anyone want me to actually run this code and no, yes, yes, okay, no. Okay, let's do this, okay? I think this is helpful in some cases because it depends on how you learn. Some people learn from abstract rules. Okay, they learn the rules first and then they just do the concrete example to confirm their understanding. Other people learn from examples. They have to see things working, examples in order to generalize to formulate the rules. So the directions are different. And in different situations, these two methods of learning, they are not, one is not better than the other one. It depends on the scenario. So it depends on the scenario, which one is more effective. Um, All right, so I'm going to do here, just a node, and then all we can do is to copy and paste. Okay, so copy and paste. Like so, uncaught example after argument because oh, okay, it's because, what did I do here? Mm, missing close paren after argument list. All right, so let me try to debug that first. Okay, so let's go back here. Probably be some kind of, okay, so new set is using a list that has f of e as the argument. Oh, because I forgot one more close paren. There needs to be one more here. And then we have the close brace, another paren, and this one is not supposed to be here. So I just did not nest everything correctly. Okay, fine. Control C, paste. Result union is not a function. Okay, so this one does not have it implemented yet. Uh, it probably has to do with the version of the node. Okay, node dash v, which version is this? And which node are we using? It's already the local one. Hmm. Does it know that? Ah, okay. Let me try this with a browser. Okay, how do we test something in JavaScript in a browser? No, no, well, close. Okay, the magic key is F12. So is it F12 or F11? Console. There we go. Okay, so now I can copy and paste the code over here. Stop, Tech, you have to stop abusing your browser. All right, so copy, go to the browser, go to the console, paste. Yes. Okay. So it would have evaluated this as well. So now we can do a console.log. Let's see whether this works. Okay, result. There you go. Woohoo! Yes. Yep. Correct. I'm making. Mm-hmm. Yep. Okay. But this is why we have programming language. Instead of verbally describe what we want to do, we have programming language that is precise because there there are multiple ways to express the same thing, but whatever you say, there's only one way to interpret it. So that's the key of symbols. This is why we use a lot of symbols in math classes, in programming, and so on, because natural language is kind of intrinsically confusing and ambiguous. All right. So are you guys starting to understand why I said part of my job is to split hair? No, seriously, okay? As a developer, as a computer science person, or as a math person, you have to have the hair splitting mentality, at least when you are at work, okay? When you're not at work, you can be easygoing, just going like, okay, there are multiple ways to interpret this statement. I'm not gonna be a little, you know, anal about this, and ask that person exactly what you mean by this. But when you're at work as a developer, you have to split hair, okay? Because if there are two ways to interpret the same sentence, the same statement, and that's your boss telling you what you're supposed to do, if there are multiple ways to interpret it, you have to clarify. Because otherwise, you can spend a whole month to deliver the solution, only that it is not exactly what your boss wants you to do. Okay, so you have to understand. Okay, to split hair, okay, I know we are digressing a little bit here, but to split hair, the first thing you need to do is to identify which hair can be split. And that is something is a skill set that you have to develop. Okay, but it is important. Okay, it's actually a very essential skill for anyone who is going to develop hair, who's going to develop code. Okay, and you can also see, okay, so this is actually important because you can see how I use that mentality to go to ChatGPT to find out that it got something wrong. Okay, so instead of just saying, oh, this is AI hallucinating, okay, which is really a bad term to refer to that kind of thing, I go back and say, okay, but why did it get this wrong? Okay, if I know how it got it wrong, how can we prevent this from happening? How do I change my prompt so that this does not happen in the future? That is the whole gist of how you can get a job and retain your job. This is the kind of skill set. Of course, people would then say, "But Tech, so why are you not making big bucks in industry and you're teaching over here?" I will leave that to your imagination. All right. So getting back to where we started off with, there we go. All right. So now we're going to the recursive case here. So if I need to find out all the possible outcomes, each one being a tuple, given T is the initial choices and we have I trials, then we can expand it to be like this. Okay, it is going to be a union. For every element in T, I'm going to generate a thing to be unioned with. So the thing that I'm generating is in the parentheses of this particular expression. This is what I'm generating. So without even looking at further detail of this whole thing, can someone tell me what I am generating here? I'm generating, well, we know it is a set because the last operation that we're performing is what? How do we call this again? Cartesian product. Okay, and what is in this Cartesian product? The left-hand side is just a set with E in it. In other words, this part here is always really just a singleton, which means it has one element, a set that has one single element, and that element is just whatever is in T. Okay, so we go through a loop for every element in T. We go like, okay, let's compute this. What is on the right-hand side of the Cartesian product? It is a recursive call. Okay, it is a recursive call, except there are two differences compared to what I was given with. Okay, the problem that I'm giving somebody else is going like, okay, let's take that E, whatever this E turns out to be, let's take that out of T. In other words, I pretend that I have chosen this element out of the bag, and this is what is left in the bag. I give that back to the next person, and I say, if I was told to remove 3 marbles out of the bag, I'm going to tell the next person to remove 2 marbles out of the bag. Give me all the ways to remove 2 marbles out of the bag. I don't care what the other person is going to do, but that person is going to give me a set of 2 tuples, and each 2 tuple, uh, well, okay, I already said that. So it's going to return a set of 2 tuples, which is basically all the ways to remove 2 marbles out of whatever choices is left. Okay, so what do I do then? I go like, okay, I chose this marble. Okay, I chose the marble that is known as E here. So I just have to pretend that there's a test tube. I put the first marble into the test tube, and then the other 2 marbles will be generated by the recursive call. So that will give me all the possible ways to choose 3 marbles out of the bag. Is that okay? So the key to applying recursion is basically to say, how do I reduce the problem that I'm given with into something that's easy for me to do, which is for each E in the set that I'm given with, pick one out of them and pretend that that is the first thing in the test tube. Then you break it up into a subproblem that has the same nature as the problem that I was given with, which is finding all the possible ways to remove 2 marbles out of what is left of all the marbles that I was given with. Yes, go ahead. Okay, it, then the question is which set we're talking about, because we have a whole bunch of sets here. This is a set. This returns a set. The Cartesian product is a set. And then the union of all of those is also a set. The big U. So the big U is returning the actual answer to this particular question, which is give me all the permutations of choosing I out of the set T. That's what the big U is going to return. With, out of whatever original marble that you're given with. Yes. Assuming I is 3 and T is the 6 marbles. Yes. Yep. It is the outcome set. Yep. It is the permutation outcome set as opposed to the combination outcome set. All right. So we are running out of time. One thing you can do to kind of help you understand all this stuff here is to incrementally increase I. We know what omega 0 looks like, so increase it by 1. Okay, look at omega 1 of 6 marbles. Okay, then you look at omega 2 of 6 marbles, look at omega 3 of 6 marbles. In other words, you are not doing this in the recursive way, you're doing this from a bottom up way. You try to figure out the answers to the easier problems and then you stack on top of that. Okay, so that's something you can do over the weekend. Or if you prefer to kind of trace this, step by step, you can do that too. Just don't start with 69 marbles. That would not be helpful, as an example. Starting with 4 marbles, choosing 2 is going to be doable. Alrighty. All right, now we can stop the